Lesson 2, Equations. Logarithmic and exponential functions. The following equality statements are useful when solving an exponential or logarithmic equation. So given that C, L, and R are all greater than 0, and C cannot be equal to 1, then if log base C of L equals log base C of R, then L equals R. As well, if L equals R, then we can take the log of both sides and say that the log of base C of L is equal to the log base C of R. We have 3 logarithmic equations here to solve, so let's start with the first one. In that first one, I have 2 logs with the same base being equal, so I can drop the log part and I'm just left with 2x minus 1 has to equal 11. This gives me 2x equals 12 or x equals 6. Restrictions: 2x minus 1 has to be greater than 0 because we can't take the log of a negative number. So x has to be greater than 1/2. And so x equals 6 is a possible solution. The last thing we are going to do is we're just going to check these because we can end up with some extraneous roots. To check, we're going to substitute into the left-hand side, and we get log base 6 of 2 times 6 minus 1, or log base 6 of 11, which is what our right-hand side is equal to. And so this solution has checked, and our solution set then is positive 6. For part B, with this log equation, the first thing that we want to do is get all of our logs onto one side. And so we have log of 8x plus 4 minus the log of x plus 1 is equal to 1. We can use our law of logs to write the left-hand side as a single logarithm. So we end up with the log of 8x plus 4 over x plus 1 equals 1. This is a base 10. And so this equation written in exponential form is just 10 to the power of 1 then has to equal 8x plus 4 over x plus 1. 10 to the power of 1 is just 10. And so I can multiply both sides by x plus 1. And I end up with 10 times x plus 1 equals 8x plus 4, or 10x plus 10 equals 8x plus 4. This gives me 2x equals negative 6, so x equals negative 3. We want to do a check and see if that solution works. So substituting into the left-hand side, I can do log of 8 times negative 3 plus 4. This is the log of negative 24 plus 4, or the log of negative 20. I can't take the log of a negative number, and so this root is then extraneous. And my solution set is empty. Part C, I'm going to start a new page for Part C. Part C started off as log base 2 of x plus 3 squared equals 4. So let's write this in exponential form. This means 2 to the power of 4 has to equal x plus 3 all squared. 2 to the power of 4 is 16. On the right-hand side, I can distribute those out, and I end up with x squared plus 6x plus 9. Making that equation equal to 0, so subtracting 16 from both sides, I have x squared plus 6x minus 7. This is just a quadratic equation that is factorable, and so we end up with x plus 7 and x minus 1. Gives us two possible answers. X can be equal to negative 7, or x can be equal to positive 1. We can check to make sure that they are within our restrictions. Within our restrictions means that x plus 3 squared has to be greater than 0. And this is true for both values. So now we can just do a check. So if I'm checking x equals negative 7, I'm going to substitute in negative 7 on the left-hand side. I end up with log base 2 of negative 7 plus 3 all squared. So I have log base 2 of negative 4 squared, which is just log base 2 of 16. So 2 to the power of 4 gives me 16, which is what the right-hand side is equal to, and so that solution checks. As well, I can check x equals positive 1. So log base 2 of 1 plus 3 squared. So log base 2 of 4 squared. Log base 2 of 16 is 4, which is equal to the right-hand side. So my solution set has two solutions, negative 7 and positive 1. Solve exponential equations using logarithms. Solve and round your answers to 2 decimal places. Okay, the first one has no logs in it, but if I take the log of both sides, I can have the log of 4 to the power of x equals the log of 605. Remember, this means that I'm using log base 10. Using my law of exponents, I can rewrite the left-hand side to be x times log 4 equals log of 605. Divide both sides by the log of 4 in order to get x by itself. And I end up with x equals the log of 605 divided by the log of 4, which is approximately equal to 4.62. Again, we could do a check for this one and should do the check by substituting in this into this first equation for x and making sure my answer is approximately 605. I'm going to skip the check just in the interest of time today. Part B. So starting with 8 times 3 to the power of 2x equals 568. First thing that I'm going to do is divide both sides by 8. Leaves me with 3 to the power of 2x on the left. And on the right, 568 divided by 8 is just 71. Now we can take the log of both sides. So this becomes 2x times the log of 3 equals the log of 71. So I've used my law of logs there as well. The next step to get x by itself is to divide both sides by log 3. So we have 2x equals log 71 over the log of 3. I also want to get rid of that 2 in front. So dividing both sides by 2, I have x equals log 71 over 2 times the log of 3. Using our calculators at this point, we can find an approximate value of 1.94. Part C. Part C, I'm going to start by taking the logs of both sides. And I'm going to move those exponents out front. So I have 2x minus 1 as my exponent times the log of 4 equals x plus 2 times the log of 3. I need to separate the 2x from the 1, so I'm actually going to distribute this in, and I end up with 2x log 4 minus log 4. I'm going to do the same thing on the right-hand side, so distributing this in, I end up with x log 3 plus 2 log 3. Getting my logs with x's involved on the left-hand side, so I'm going to move this to the left, and I'm going to move this log to the right. So I end up with 2x log 4 minus x log 3. And on the right, I have 2 log 3, and that one becomes plus log 4. On the left-hand side, I have a common factor here of x. So if I factor that out, it will separate it from the logarithms. I'm left with 2 log 4 minus log 3. The right-hand side is not going to change. So these get some of them can get fairly long with lots of steps. To get x by itself, I'm going to divide by those brackets. So divided by 2 log 4 minus log 3 on both sides. I end up with x being equal to 2 log 3 plus log 4 over 2 log 4 minus log 3. Once the x is by itself, I can go to my calculator. Substituting into my calculator, I end up with an approximate answer of 2.14. Remember, you need to be checking these answers by substituting that value back into our original equation. Next example is to model a situation using logarithmic functions or logarithmic equations. Paleontologists can estimate the size of a dinosaur from incomplete skeletal remains. For a carnivorous dinosaur, the relationship between the length, s, in meters of the skull, and the body mass, m, in kilograms, can be expressed using the logarithmic equation. And here it is. Determine the body mass to the nearest kilogram. So we're looking for m of an Albertosaurus with a skull length of 0.78. So all we're going to do is substitute in 0.78 for s. So we have 3.6022 log, and instead of s, we're now putting in decimal 78, equals log of m is what we're looking for, minus 3.444. Start by trying to get that log by itself, so we're going to add that 3.44 to both sides. So we have 3.6022 log of decimal 78 plus 3.4444 equals the log of m. Simplifying that left-hand side works out to 3.0557 is approximately equal to the log of m. Remember here that this means that we're using base 10 since we don't have a base written in here. So this is the same thing as 10 to the power of 3.0557 is approximately equal to m. This works out to about 1,137 kilograms for the mass.